So, hi Freda, can you hear me?
Yes, sir.
Hi. Shall we wait for some time for some other people to join, or should I start? What do you think?
So it's up to you. We can wait for about 5 minutes.
That would be okay. Uh, do you want to introduce yourself? Maybe I should go first. Uh, yeah, so you were not probably there last time. I'm kind of a teaching assistant for this course, uh, and I'm a doctoral student at the Indian Institute of Science, Bangalore. I'm in my fifth year, and yes, so we're going to discuss few things uh, on finite element methods today. I'll take some questions if you have any. And yeah, would you like to
Uh,
go? Yeah.
yes, I am a teaching faculty, assistant professor at Don Bosco Institute of Technology.
Okay.
Also, at the same time, I have a teaching experience of 22 years. I'm a
Mhm.
PhD scholar at Assam Don Bosco University.
Okay.
And I'm from electronics background, electronics and telecommunication background. Majorly, it is microwave engineering. So
Okay.
I work with simulations tools which involve FEM
FEM.
and yeah, finite element method like ANSYS.
Mhm.
Uh, and so I'm looking towards using more of tools, in a better way because I lack a lot of knowledge regarding
Mhm.
this. But I would want to know, sir, from you, you are having these courses online or are there lectures like recorded lectures every week with assignments? So I have missed one, you said.
Mhm.
So, so how do I cover that up?
Yeah, so these are like pre-recorded sessions. I think you must have gone through the website, right? No?
I have gone through the website, but I'm not very familiar with that. I was not able to locate I have done an NPTEL course some years back, but
Mm-hmm.
uh, the plan used to be that the lectures were always there,
Mm-hmm.
and then there were always assignments there week wise.
Yes. Yes.
So so that's
It's
the
very
pattern, right?
it's very simple. Yes, it's exactly the same thing now as well. These are like rerun courses. So like the course the it's this is not the first time the course has been offered. Probably long back the course was recorded. And so they're just rerunning the course for people who have not like taken the course before. And so everything is available online. Yeah, everything is available. The content for
So
the next
so
week.
I
Yeah.
can attempt the missed assignment, is it?
Yes, yes. I think yes, you can. Wait. So there is a deadline. You must be receiving mails from the NPTEL team.
But I think I
Probably
just
there's a
registered. Yeah,
you just registered, is it? Probably then you
yeah.
might have you would have some we'll have to see. You try to attempt the attempt the quiz. Anyhow,
Okay,
that does
okay.
not matter as long as you're able to grasp the things. The first week was also not much, very intensive also. So maybe you can just directly attempt it if. But I think these TA session, like my session, the next day of my session is the deadline. I have done a a previous course similar to this one, and that in that one, the deadline was like a day after my session. So they usually plan a live interaction session just before the submission deadline. And yeah, so that if someone has a question in regards to the assignment, they can discuss it and then just submit
Okay,
it like that. But
okay,
probably
okay.
it's a little
This
different.
is my first. This is my first mail actually.
Okay,
That's
that's why.
why
That's
yeah.
probably
So
not. Yeah. Hmm.
so I don't even have clue of what is to be asked. I have to go back and check, sir.
Yeah, that's fine. I think NOC25. So let's start. I'll just quickly introduce. This is not the right one. Wait, to change the title. So this is the uh, previous course's name, which I had done before. So this is applied numerical method. Right? That's the name of the course, right?
Yes.
Yeah, and we are in the second live interaction session. Let me do one thing. I'll quickly also go through what we had done in the previous session, which was last Tuesday. Um, that was like we were trying to cover. So what we were doing was we were trying to cover just a glimpse into applied numerical methods. And just like how you're interested in finite element methods, the thing is, last time a couple of people who had joined were also interested in finite element methods and just wanted to know what is exactly happening in the background of their simulation software. What is the essence of it? But turns out that this course is not a finite element intensive course. Rather, it is a maybe I should say this is a this would be a prerequisite to a course which would offer like something on finite element analysis. This course, a lot of things which we are going to discuss is something that will be required when we go into intense finite element method. But anyhow, last time also people were trying to identify that there are other finite approximation methods also. So like finite difference method or finite volume method. And so I thought let's debunk this difference in the three approaches. Um, in the very starting of the course, so that later on we can focus on the week's content rather than going into these things. So the thing is, yeah, so let me just quickly recap what we had done last time. um, so this was my introduction. I asked for some questions, and yeah, so there was this overview. See, you can go through these course content, this course overview type of things, and the syllabus of the course, what topics are going to be covered in this course. You'll recognize that we do not directly deal with finite element method, but there are a lot of things that we need to pick up before we get into any finite approximation methods, and this is what that course offers. Um, so last time, because I understand that you're from electrical background, you might not even be aware of finite difference or finite volume. Probably, maybe you are aware of it already, given your experience in teaching. But anyways, um, so these are I believe these things are they originated from a mechanical background. So anyways, uh, the thing is, last time what we discussed, or like how the professor introduced the course in his first week, was he introduced root finding algorithms as a glimpse to numerical methods, and this is what the first week was. I saw the second week was a little bit into introduction to computer programming. Um, while I can take few sessions, discuss, and we can do a few coding exercises, coding assignments, where we can get more acquainted with a hands-on session on coding. I thought I'll not spend this week on that. Rather, I thought we'll discuss a little bit on finite element and finite difference methods. Anyways, this overview itself, this week wise breakup of the course content is quite satisfying for me, because it very nicely shows that actually numerical method is a bigger umbrella than any finite element or finite approximation study. And what essentially uh, so if I do a finite approximation method study, what the umbrella we are looking is week 8's content, where we are seeing solutions of partial differential equations. So that is where these finite approximations come in. This we will see in more detail in the course of our this session. Soon we'll see that. But there is more to numerical methods. Um and essentially, whatever we, and this is, I'm trying to recap that this is something which I also iterated in the last session, that whatever we are going to do in the first 7 weeks of this course are in some way is gonna be in some ways helping you in again solving PDEs. So the big problem in so essentially what we are doing is we are solving a continuum mechanics problem, and any continuum mechanics problem becomes a partial differential equation. If and that becomes a governing or constitutive equations. Any conservative law or any constitutive law, if we write it mathematically, becomes a PDE. And and so we'll see that the approach of solving a problem using numerical methods is to break the problem, the big problem, which is spatially distributed, it is distributed in time domain also, into a large number of elements or large number of nodes or uh, large number of volumes, essentially saying that breaking a continuous field, a multivariable continuous field, into a lot of data points. So rather than storing function given as in terms of x, y, and z, we'll store a value of f of x, y, z at all x, like at different x, y, z values. So that is the essence of solving PDEs, or finite element, finite approximation, or finite difference methods. And essentially the content of the first 7 weeks is gonna be prerequisites to PDEs. Uh, in the next few weeks, we'll do some advanced topics in numerical methods. Again, nothing very intensive there. Yeah, these are like some extra topics. This course is like a what do you say? It's not a it's a starting course in numerical methods, so that's why they don't go deeper into PDEs and just uh, touch upon it and then go ahead and discuss few things like optimization methods and artificial neural networks. You see that a discussion of only 1 week on ANNs again is not enough, but that is how the course is defined. It is like a starter course, an introductory course. So then I had discussed the same thing. The week-wise content is graphically uh, shown in the reference book the course mentions. So I'll just show the reference book. There are two reference books actually mentioned in the book in the course content. I just explored the first one. If I would need the second one as well at some point of time, I'll go through it. But the first one itself seemed quite nice. So the core book's name is Numerical Methods for Engineers, and Stephen C. Chapra and Raymond Canal are the authors. You can find this book, and on in the first chapter of the book, they very nicely summarizes the content of the course. uh, the first few chapters are on root finding, then on solution of a system of linear equations. You can do optimization also. That also comes under the umbrella of numerical methods. You actually, again, discretize your domain, find the point at which the solution is minimal, or there can be another approach also. Again, not discretization is not the only solution. Then curve fitting and regression is another thing. You would need integration. Um, Integration finds its direct application in solving ordinary differential equations, which are like the simpler of the differential equations. And then when you get into PDEs, there are these finite approximation methods which kick in. So that's that thing. What I had spent my rest of the time in the previous week's content was was on this square root algorithm to just showcase how a numerical method becomes a numerical method. And this Bhakshakali formula is from an ancient script that we so hi Yashod, we are just recapping the previous week's content, and we'll just
Hi,
get
sir.
on.
Good evening. Sorry, I
Yeah,
was a bit late.
that's
My network
that's
connection was
okay.
not proper.
Yeah, that's okay. Yeah, that's fine. So again, as I was saying, this Bhakshakali's formula was a very ancient mathematics formula, which very nicely um, captures the essence of a numerical method. We discussed the divide and average. I'll not go through this formula again. It will take some time, but the essence was that essentially we could derive this formula as a numerical scheme where you just and the scheme could be called as divide and average, or the Heron's formula. Again, Heron's method is historical name given to the text because of the text. These formulas were found out, and what we saw was this Bhakshakali form method or divide and average was a Newton-Raphson scheme in disguise. So Newton-Raphson came very late, and the form and the time at which these formulas were derived, and Newton-Raphson was not in the picture. But later on, we can see that these are mathematically equivalent statements. So again, not very they are not very important, but they demonstrate an important point. That is what this was discussed for. Just for the sake of maybe just for the sake of let me open it and let me just show, just for the sake of discussing the animation, let me just run this and show you the animation of this divide and average method. So essentially what we are doing there, while my animation runs and saves, i I will just quickly tell what we are doing. So we want to find the square root of any number. That is our intent. Now, divide and average method tells you to guess, take an initial guess, find the inverse of it, like inverse as in you find s by guess. So the actual under root of s would have the s by guess will be the guess itself, right? Because it's a square root of s. You average these two numbers, and this becomes your next guess. So you keep doing that, and um, in some iterations you approach the solution. So that is what this is about. um Let me see if my animation has run. It seems it no, it's still taking some time, but I'll just quickly show that to you. So let it run. People, so you guys are aware of Jupyter Notebook, right? I saw that professor in his recorded lectures has actually used Jupyter Notebook, so I didn't thought like I think it's not necessary to go through this Jupyter Notebook stuff and how to install it and how to use it. It's pretty simple, straightforward. Yeah, so I think now it is working. So let me close this and open this divide and average animation. So let's see what it does. Essentially, we have three curves at any point. We take a guess, find so it's quite fast right now, but essentially what is happening is you take a guess, you find the a square by x value of it, average it, and then take the next guess. And this is how you sequentially go near the square root of it. So maybe it will make better sense if we quickly go through the last week's content. But I just wanted to show how this numerical methods work in action. Okay, so I'll just close it. Okay, just close it quickly. Let me see. Just in the interest of, yeah. So what essentially we are doing is y equals to x line. This is the blue line. At any point we take a guess. This is our guess. X equals to x0. This orange line is the under root we want to find. Say the number we want to find the under root of is a square. Okay, so a square by x we do. We find the value. We find the average of it, and this becomes our next guess. So at the next guess point, again we do the same thing. And what we you will see is you keep approaching to the square root of it. That is what the thing is about. That's it. So nothing fancy there. Let me see. Yeah. So this is the frame where you see that this averaging happens. So this is the average of these two numbers on y-axis. This is the half midpoint of this line. And so you move to the next guess and you approach the square. So you see at the point at which a by x square and y equals to x meets, this will be the point of y x. This will be the point of y equals to x equals to a, which is the under root of a square. Anyways, so this was something which I had discussed last time. I'll close this. Before going ahead into the today's content, Yashod or anyone, do you have any questions for me to discuss?
So, as of questions, I don't have any questions. But
Mhm.
just I want to ask, like, what is the topic of today's discussion? Can you brief it?
Yeah. So yes, let's go about that now today. So, as we had discussed last time also, we saw that a lot of people had joined the course with an hope that we can get as much as knowledge about or intuition about how these finite approximation methods work, how come they're different, and this is something which I briefly touched in the last session also, where you compare um, different methods. So for that, actually, I wanted to just recommend a paper which I have actually used for today's content also. What we are going to do today is look at the three finite approximation methods. This is the course. I'll try to put it up on the shared folder. So those of you who don't know, you will be shared links of these recorded lectures of the sessions we are having. I'm actually recording the session, and these will be put up on YouTube, and you can go through them if you have not joined a class. And accordingly, every time like I refer to some content on my computer, I'll put that up too. So these notebooks are also being uploaded on that a drive folder that is gonna be that is gonna be shared with you. So that is something that you can look through. So today what we are going to do is um, I have to break it to you that this course is not finite element intensive, or for that matter, it is also not intensive in finite difference. But in the course of today's lecture, what we'll see is finite difference is so straightforward. It becomes so intuitive that even this course will have you will see that a lot of times whenever we are going to solve differential equations, we are going to resort to finite difference because that's the most straightforward finite approximation method. Uh, so today, just to answer your question, what we are going to do is we are going to implement a very simple problem in using the three finite approximation methods, which are the finite volume, finite difference, and uh, finite volume method, and finite element. So I don't know, did I say all the three of them or not? Okay, finite
Yes.
volume. Okay, finite difference and finite element. So that actually I had also prepared one text like a tutorial kind of thing. Let me see if I have it there. Let me see. Yeah. So I was trying to document the content of what I was gonna discuss also. Just to, yeah. So this is what we are going to follow today. This is for me to actually refer to while we are discussing these things. But I'll see if I'll try to complete this up and also put it up. I'll see if I'll try to put this up as well. Now today, when we discuss this, there are few things which I want you to note. First of all, the focus will not be on coding, although we are going to write codes again. Like we are going to write codes today. The focus is not going to be on how to write the code. That has become trivial in today's time. Uh, the focus will be on appreciating the differences between these methods. And the third thing is uh, appreciating that even this is we have actually jumped straight to the week 7 of the course, week 8 of the course, when we are trying to discuss this thing. Actually, this is a misplaced session, to be honest, because what we you will note is things which we don't know how to, uh, presumably we don't know how to deal with, are just skipped. So I'll show that to you. And so essentially saying that there are when we are going through these we'll solve this. So what we are going to do today is we are going to solve this and this 1D conduction equation. Let me zoom in. We are going to solve this in this heat conduction equation. So essentially what we are, so system is, let me draw the system also for the benefit of everyone. So you have this rod, and this is a 1D rod. Okay, this is a 1D rod, and you know there's a temperature at some point at one boundary, and at the other boundary there is another point. So I'll write it as T left and T right. And because of, let's say, there's an electrical wire uh, inside this rod. Let's say there is an electrical wire going inside that rod, and I don't know. Um, So, okay, fine. So there is an electrical wire inside this rod, and you are having, and this has a varying conductivity. Sorry, resistivity. Uh, so resistance is R, okay, in the right now, and it has a varying resistance, and you're flowing, and there's a potential, there's a electrical potential across this wire. So what essentially you are having is joules heating, which is varying with space. So joules heating, or Q dot, will be I square R, and we are I square R, okay. But I'm not going to go into the yeah. So I'm not going to go into the electronics, the electrical part of it. I'm just gonna say that this is this. So we have a given heat generation quantity, that in this rod there is a heat generation term also. And as you know, the heat is gonna be conducted from a source, from a space of high temperature to a region of low temperature. Um, and so when we do that, so essentially what um, equation we will have is um, that K, wait. So the equation we will have is something of this sorts. Okay, let me put this thing there. Okay, or Q dash only, right? Watt per meter. What? Q. Let me think. Yeah. So you will have something like this. A. A is the cross section area of this bar. Okay. So this is the geometry that we are going to deal with. Now, a lot of things right now, which we're just quickly skipping. AC, there's no X. There's a cross section. K is the conductivity of the thermal conductivity of the rod. So this is a thermal problem, and essentially the problem is, if I want to name it, it's 1D steady state. It's steady state also. Mind that we are saying that there are no transients involved. Heat conduction equation. And if we have to derive this equation, if we have to derive this equation, uh, what will we say? How do we derive it? This is energy conservation that we are going to do. So maybe people are not familiar with the thermals background, because I see that people from non-mechanical background are also present. So maybe we'll quickly discuss this aspect of also conservation of energy. Okay. And so what you are saying is you look at a very small control volume in this pipe. So say we are just interested in this element of it. So let's this is where we are interested at. Okay, a small volume, and essentially there is some energy that is going to be generated in this volume, right? Which we are saying is generated by this joules heating, let's say. Maybe I've not given a good example, but let's say this is it. So this will be the energy generated um, in this small volume. This has to be dissipated, right? This will have to be dissipated again in the left, in the right. Um, let's say so now we will have to actually, so this is energy generated. Okay, energy generated. Okay, um, now conservation of energy says that this has to be diffused, not dissipated. Well, we can't say dissipated, but diffused. This has to be diffused. So conservation of energy says what? So energy, because we'll say that the energy of, because it is steady state, we'll say this, that dE of volume, this control volume, I say control volume divided by dt is 0. And now if in a general case, what will this be? This will be E generated um, plus E transfer, E heat transfer, or E conduction, right? Some heat will be conducted away, or some heat would be getting conducted in, right? So that we'll have to that should, this term has to be 0, right? Note that the this plus sign is essentially saying that whatever heat is coming inside, see, E generation term is also going to increase the energy. E generation term is also going to increase the energy of the control volume, and so will the E conducted inside. So E conduction means the energy conducted into the system. Okay. Now, in order to write this e-conduction, we will have to invoke Fourier's law. Fourier's law of heat conduction, which says that across any cross section, uh, across a temperature gradient, um, the heat transfer is of this sort. So you write it as this. For some of us, it will be quite um, simple. But for others, it might be complicated. So just we'll go quick. We'll quickly go through it because again, this is not the important part, but still. So this is the thing there. And now, how do you write E conducted here? Okay, how do you write E conducted? Actually, these should be E dots. Okay, these should be dots. Even this should be dot, right? To maintain the dimensionality of the equation, this should be power generated. It's not energy generated because then if energy generated, then delta T will also come. So time into time will also come, right? Amount of time over which you are generating energy, it's actually power generated. So we are saying energy per unit time that is being generated. So this is actually so I think this is not right. This should be d by dt, right? This should be something of this. Because Vi is energy, right? Yes. So Vi is energy or Vi is power. No, Vi is energy. That's okay. Yes. So, anyways, again, going back to this power getting conducted. Okay. So how do you write this? Essentially, you will note that this has to be energy. So essentially, what we are saying here is that let's say this is the control volume, right? And locally speaking, we can say that the temperature is a linear profile here. Let's say locally, right? There will be a temperature point here, which is this one, right? This will be T of our control volume, but to the left of it, there will be another temperature, and there will be another temperature on the right of it because this is a 1D problem. So what essentially we'll note is that heat is getting conducted away. So in this case, if we assume this profile, this profile can be anything. So actually, to be more precise, it can actually be just to be more accurate. Actually, we can say something of this sort. Okay, let's say temperature is of this is the temperature profile. So right. So what you will note is that E dot conduction. So here you see, uh, you note that energy is getting conducted away from the left hand. On the right hand also it is getting conducted away. Suppose this is the situation. So what do you write? You will write Ka T of my control volume minus T of my left hand side, control volume left hand side, divide by delta x, let's say some delta x, right? And then this is losing, right? As I told you, this the way we wrote E conduction was in the format that heat is getting conducted in. Mind that. So in that regard, we'll have to write this. This in this format it is fine because here we are saying that heat is getting conducted away from outside to inside. Yes. So actually, the actual Fourier transform has a minus sign also. So it says that in the direction of opposite in the direct. So the Fourier's law is actually this. Right? So a lot of things have to be covered before covering this part. That's why Fourier's law of conduction has this negative sign also to demarcate that the heat transfer happens in the opposite direction of temperature gradient. Heat transfers from a sensor from a region of high temperature to low temperature. So for in that matter, um, when we write this term, actually we'll have a minus sign here. So I'll absorb that minus sign here to here, right? And similarly, again, same thing on the right hand side. This will be this term, right? What you will note is, let me take this minus common here. Okay. Okay. Let's not do that. I'll go one step ahead and write this term. Now, can anyone tell me if I want to write it as dt by dx control volume? Can someone tell me what is your guess? Um, is it dt by dx or dt minus dt by dx? So this will be minus dt by dx, right? Or let me put it as, rather than saying this thing, let me put it as x minus, right? Um, right. This one will be dt by dx at this will be x plus, right? So now, wait, there is another thing to note. When you say this is q dot, okay? This is q net. Let me put that also. Okay, or q conduction. Here also we can say q conduction. Mm, okay, so now we'll substitute these things there. Okay, so if I do that, and I'll also write ECV also, let me write ECV also. Mm, right, no, let's not write ECV. What we have is this thing has to be zero, okay? So if this I'm just doing a simple energy balance. There is nothing very fancy or very actually I'm doing it very loosely also here. I'm not doing it properly also. So this is a very loose derivation of this equation. Okay, the equation that we are going to solve today. Uh, what you see is that there's a delta x coming in, right? If you divide everything by delta x, what you will have is, let me put it this way, by delta x, right? Now, again, note that what is this term? If I just take this inside, not inside, just on the other side, you see that this is essentially this term. right? In the limit delta x tends to 0, we can write this. Again, AC and AC will also get cancelled. That is also important. AC and AC will also get cancelled. So this equation does not have should not have a AC term here. Then what else? So I will keep it for myself just to, yeah. And yes, there should also be a minus sign here because the way we have derived it is there should be a minus sign. So this is the governing equation that we are going to solve. This is a simple 1D problem. The important thing for us to take from this slide is that any problem, no matter what the engineering field is, essentially at some point of time, you're going to solve a differential equation of some order and some degree, right? We're going to solve a differential equation, and we are going to look at the three ways of solving differential equations. Uh, Today we are solving not a partial differential equation, it is an ordinary differential equation, but but finite element or finite difference or finite volume methods also find their they find their better use in finite uh, PDE. So this one is OD right now, and we are going to demonstrate the three methods using this ODE only. Okay, but yeah, so there is no difference, however, if it's a OD or it's a PD. Essentially, it's a differential equation only. Okay, now I'll also write the boundary conditions also. Okay, and also I have been given what is the form of this Q dot. Okay, so I've been told that if I take this K on the other side, on the right hand side, okay, then this becomes as uh, some TA, some T A minus TB divided by L square e to the power x squared. So this is the form which is given to us. This is a given differential equation. Okay, there is no derivation there. And two boundary conditions that T0 is TA and TL is TB. So one thing which I did not do, which is incorrect in the previous slide, is define the coordinate system, which is like the first thing I should have done. The coordinate system starts from this. This is my origin. Okay. This is my origin on the left hand side. And on the right hand side, it is x equals 12. So length, the bar's length is L. Okay. Nothing very fancy. And I'm just writing it somewhere. Fine. So this is the equation that we are going to solve. Okay. Again, we don't want to deal with this temperature, this context of thermal 1D heat conduction equation or anything. What we want to look at is primarily what is the form of the energy. I'll also switch on my camera, not switched on my camera, so that you guys can also see me. Yeah. So essentially, we don't want to go into, no, it's a problem which is a very biggest problem. It is not a thermals related problem. Although what you will, I should also point out, then whenever we have this kind of situation, whenever we will have such kind of situation, dy by dx is some function of x. This is called a heat conduction equation. This is a very primitive thing which comes from in partial differential equation also, or even if you take up mathematics course, you will note that these type of equations are called the heat conduction equation from the primary reason, as I showed it to you, that essentially heat conduction is defined by the double derivative of the temperature field. But no matter what my dependent variable is, essentially what I'm going to do is I'm going to solve for a differential equation. So just to remove the connotation of this temperature and anything, I'll non-dimensionalize everything. Okay, so I'll non-dimensionalize everything by saying that TB by TB, let's non-dimensionalize T by writing uh, by defining a new variable theta, which is like T minus TA. Becomes T minus TB. Okay, so this one, what it does is it transforms the boundary conditions to at x equals to 0, this will become 0, and x equals to 1, this becomes x equals to L, it becomes 1. We'll also non-dimensionalize x at this point by a capital X, okay, and this is x by L, so that our domain becomes from 0 to 1. Again, 0 to 1 is our domain, okay, that is where we are going to solve it, everything. And so what you will note here is the equation becomes e to the power x. Let me rather than using x, or let's use x only, that's all. This is what the equation becomes, right? No, let me just check. Yes, the equation becomes in. So it is given, actually, just let me quickly point this. I'll remove this part. This is our governing equation, okay? This was the governing equation we had. Q dot is given to us that it is of this form. Okay, this is something given. Let me write that also. Given. Okay, and remove this here, so that what we have is this. This is the energy, this is the PDE that we are going to solve for. Okay. Okay. So now let's first discuss finite difference method. Okay. Uh, Let me just quickly see what are the important points that one wants to emphasize when discussing a PDE. Okay. Okay. So let me first draw how do we deal, how do we, so what is the philosophy of this PDE? Okay. So right now, what we have is, essentially speaking, what we have is we have a function. Give me a second. Yeah. So this is 0. This is 0. This is our domain. So let's, the domain we are interested in 0 to 1. Okay. And there is some theta, right? Theta of x. And there is this x. We don't know what theta of x is. Probably some curve. Let me draw some curve, some random curve. But we know that this, whatever the curve is, it will satisfy this boundary condition and this boundary condition and this governing equation. Okay, so just to emphasize that the boundary conditions are matched, we know that theta of 0 is 0 and theta of 1 is 1. Okay, I'll also mark that also. Let's do that. Okay, so this is also 1. Just highlight that this is a dash. Okay. Okay. So this is what we are solving for. We want to find the functional form of this function, this functional form of this theta of x, or the function itself. Okay. Now, what do we do? Uh, any finite approximation method for that matter will break the domain. The domain means x equals to 0 to x equals to 0 to 1 in certain manner. Depending on what the approximation method is, they will break this domain into either a finite number of nodes. So in finite difference method, what we do is this 0 to 1 is broken like this. Okay, I'll show this to you. One way. So what is done is we break this domain into a lot of nodes. Okay, lot of nodes. Okay, let me just quickly draw this part. Put dot dot to emphasize that there are a lot more points here. Okay, so and I'll also mark them as I equals to 1 or I equals to 0. Then this is I equals to this is I equals to 2. And depending on how many discretizations you do, how many points you break them. So this is called, this you can call as the fineness of the mesh. So we are kind of making a mesh out of it, right? We're making a mesh. But mesh is actually not the correct term when right now let's not use the word mesh. Let's use the number of nodes. Okay. The philosophy of finite difference method is it says that uh, rather than finding the solution in the entire domain or finding the function in the entire domain, what we'll do is I'll write this part rather than finding the function itself. Let's find its value at the nodes at the locations we are interested in. Further, any function, or let me put it or we can approximate at the end of it, all finite methods are approximation methods. Okay, or we can approximate uh, any function by a series of its value at different points in the domain. That's the essential. That it might seem very trivial to you right now. Okay, it might seem, yeah, that's very straightforward, but it will, this statement will become very handy um, when we discuss other schemes. Okay, this is the principle, this is the philosophy of finite difference alone. Okay, very unique to finite difference methods. Finite volume and finite element methods have a different philosophy that will help us to understand them too. So we'll do that. So you get this point, right? Everyone understands this point. Rather than finding the function itself, which we can do analytically, we would need to do and that analytically through calculus. If that is very complicated, we'll find functional values at different nodes. So theta of x is, let's say we write it as series of xi's to series of theta of x. So if we have just this one-to-one relation, rather than finding the entire function, we are not going to find an entire functions at a lot of number of points. We will just find the value of this theta. Okay. Now, how will you do this? How will you find theta at different xi values? You will state that at any xi values, this thing should hold, governing equation must hold, and the boundary conditions must hold. That is what you're going to do. Now, because you don't have an analytical formula for this function, and you want to find theta of xi. So essentially, what we are going to do is, how do I find this? Step zero is step zero is uh, enforce. Let me write this as. So anyone has any questions or any comments right now? Okay, this is our step zero.
No, sir.
Okay, everyone is following that part is clear. Whatever I'm saying.
Yeah. Yes.
Yeah, and no need to call me sir or anything. Can call me Shrey. That's okay. So this is step zero. Okay. Now it's actually very straightforward. I'm taking too much time into it, but let me do that in the interest of and I'm doing it preemptively because later on when I want to draw the contrast with other methods, this uh, emphasis will come handy. So the step two is in order to enforce the PDE or the governing equation or enforcing the differential equation, we need to approximate derivatives. That is what we need to do. Okay. So this strategy is very unique to finite difference methods because other methods are not well. Finite volume methods also approximate derivatives. It also involves um, approximating derivatives. But as we will see, finite element method does not work on this philosophy that first of all you find the values at a given number of nodes. That is very unique to finite difference. Then it does not approximate derivatives. That is also something that finite element does not do. Okay, and these small details actually make different functions uh, like convenient as per the situation. So as I said, if you want something very fast, if you want to solve a problem which is simple, which is not very complex, and you want to find the solution to it very fast, then finite difference is the best method because it is very straightforward, as we will see. And so the second method is approximating the derivatives. No, sorry. So this is what you need to find. While so finite difference method is very straightforward, it can be implemented very quickly. Even we can write quick very codes of ourselves. But finite element or finite volume for that matter are better if you have a more complex problem or the domain is more complex. Then it becomes better for us to implement finite element. We'll see soon. Um, and even then, it turns out that if we are dealing with conservative laws, right? We want even see, we are trying to model something, right? At the end of it, if we are trying to solve a problem, we are modeling it, right? This is a mathematical model of our 1D bar or whatever. We want the model to satisfy some important laws, right? Finite difference does not enforce that the conservative laws are satisfied. So even though this is the conservation law and this is what we are implementing, at the end of it, at this step one, we will approximate it. And at that point itself, the exact satisfying of the conservative law will break because we are approximating it. Okay. So finite volume methods will come in handy because they take care of this aspect of it, that we want, no matter how fine the mesh is or how coarse the mesh is, the error in our the residue or the error in our governing equations is zero. Whereas finite difference method require you to have a um, sufficiently small finite, sufficiently small steps or small discretizations to enforce that the governing equations are satisfied by a are satisfied like they're maintained, or they're satisfied satisfactorily. Okay, so that is something you will see. Okay, so this is the approximation, this is step one. Okay, and now this is something that we need to discuss. So how do we approximate things in finite difference? Let's do this. So again, uh, yeah, let me remove few things here. Let me not, yeah. So this is step one. So, and finite difference uses Taylor series approximation, which is the best bet we have got, right? That is the most straightforward thing we can do. We can estimate things like, see, suppose you are at this situation. Okay, something which I didn't mention properly is that because uh, of this aspect, see, at the end of our uh, at the end of our what do I say? At the end of our method, essentially what we will have is a series of xi values and a series of theta I values. So what we need to do is approximate this thing with only these terms, right? Either series of xi's or theta of xi's. So at the end, we are going to find some certain theta, certain values of theta at certain xi's. We need to approximate this term using these theta I values only, theta I and xi values only. And there the Taylor series approximation comes in. Okay, so actually we write that suppose you are at some I location. Okay, so this node, the one which is on the left, we may write it as I minus 1, and then this can become as I plus 1. Okay, so now there are different ways of looking at this thing. Uh, you can write that theta of how much time do we have? Okay, xi plus 1. So everyone would be aware, like they remember Taylor series, right? I don't need to properly write it. But anyways, it's very similar. Once I write it, everyone will remember this. So not a problem. Okay. So theta I will be d theta by dx at xi into xi plus 1 minus xi, right? And then you have this term. So again, I want to point out that we are skipping very ahead of ourselves. This is something that would ideally come in step 8, but I saw that a lot of us are coming in this course with a motivation to explore finite approximation methods, and because we are in the early weeks of the course content is not very technically rigorous. I thought we can spend some time on these things without wasting these hours. So yeah, so a lot of it we are skipping. A lot of it, will come in the future uh, weeks lectures. You'll see that a lot of things will come later on. But anyways, we'll go ahead. Does not matter. Very simple stuff. Okay. So the second term will have half d square dx square, and this will be square term, right? This is the Taylor series approximation. Now, there are different ways of approximating things. We can actually, if you note, we can approximate, I don't know if we can approximate double derivatives or not. Yeah, probably we cannot. But there are things called as back forward difference scheme, backward difference scheme. There is a central difference scheme. Those things are these are uh, devils in the details. I'll not go into it. Just demonstrate one scheme, the central difference scheme. So the way we find or approximate this term, essentially what we are finding is, let me also point that out. We want to find this. We're finding this double derivative at a given I location. If we can find it at a given I location, we can find it for all i's, right? So this is what we want to find. So now we'll also write the Taylor series for xi minus 1. Okay. So this is fine. This will be xi minus 1 minus xi. This is also okay, and this is xi minus 1 double square. Okay. Um, Now, right. Okay, one more thing is that yeah, one more thing is that because we have considered this is a uniform mesh. So xi plus 1 minus xi is xi minus xi minus 1. So in that sense, if I just, rather than putting this thing here, if I say, I'm just changing the signs of these things. Okay. I don't need to change the sign there, but still, let me change there also. The square, so that minus sign can just be ignored. Okay. So with that, let me subtract these two equations to get what? I'll get theta of xi plus 1. Did not want to derive these things, but let's do it. It does not matter. Uh, what we will have is, we will have these two things will just, so this will be 2 theta right? And then you will have this term there. Into, let me also write this as delta x. Okay. So that I don't have to write it again and again. Okay. Now you see that now this one becomes, so now we have approximated these things. So what essentially I have here is, these a values and I values are, let me write that. This should be plus, this should not be minus. mistake. My mistake should be plus, because we have added the two equations. We have not subtracted them or anything. Right? And this, the denominator will be just this. Simple, right? Okay. So now we know this. Okay. Mm. Again, one more thing is uh, okay. So this is there, and now we substitute this in our step 0, which is enforcing this term, right? So let's enforce this. So if I do that, this is equals to this. So let's discuss this. Are we clear that this is the finite difference scheme, right? Do you see the problem gets solved at this point? Does anyone have a problem of how to proceed next? I want to discuss this part here. I want to talk to you. So do you see that now there is a question of how do we, from this, how do we proceed? But all this part is clear, right? Up till here, everything is very clear.
Yes.
And I have emphasized too much into it. We could have just written this very quickly in, let's say, 5 minutes, but I have taken more than an hour discussing this part of it. But you know that this is not very difficult to write. We can quickly write it. Problem number one is how do you deal at the boundaries? How do you solve this at the boundaries, first of all? So the thing is, the scheme which we have used, the central difference scheme, requires you to always have a node on the left side of it and also on the right hand side of it, which the boundary nodes, this is a criteria which boundary nodes do not satisfy, right? But luckily, we have these two boundary conditions there that we already know theta values at the boundary nodes. Okay, so we know that this equation is something that we are going to only um, enforce at the interior nodes. So I didn't mention that in the step 0, but let me write that finite difference schemes, uh, finite difference scheme uh, enforces PDE only at interior nodes. This is important, but that is a detail in that is a devil in the detail. It might not affect us at this point of time, but it is an important thing. It enforces PDA only at the interior points, at the boundary points or boundary nodes. Um, uh, Boundary conditions are there to get satisfied, right? Now, how do we proceed from this point? This is the second problem that uh, we have a problem there, right? What what is the problem here? Let's look. So let me make a. So there is a problem here. Yeah. So what is the problem? Let's see what is the problem at this point. So now we are into the computational aspect of it. How do we solve this? So we have a series of unknowns. See, we have what we have done is earlier we didn't know what was theta of x. Theta of so unknown was, yeah, someone has a question. Yes, probably not. Think they must be trying. Were you just trying exploring that hand raise thing, or do you have a question? Oh, there's a chat. There's a message. Can you take a simple real life problem where it explains Yeah, Bhanu. So that is what. This is a very simple example. So would you like to talk? Would you like to tell? Uh, would you like to say out loud your problem, like your comment? Uh, we can discuss that part of it. So probably not. Probably not. But let me again give an overview of what is going on. Why the so So the reason I cannot, or maybe I can, is take a simple real life example. I can do that. But the important thing to note here is, Bhanu, that no matter what the problem is, any real life problem. So this real life problem, the problem that I had taken was a heat conduction in a bar. The important aspect of any finite approximation method is essentially it will solve a differential equation. That is the important part of it. So no matter what problem I take, we will end up at a differential equation, which I think in a loose colloquial sense does not remain a simple statement or simple problem. Once you get into differential equations, this is as simple as you can get. Maybe you can go one step ahead and take this as zero, and this would be simpler, but again, that does not matter too much. That is not a very large amount of complexity added. So no matter, so essentially, I want to just point out that maybe we can do it even simpler, but then we will lose any touch of it. And I also didn't want to give an overview of all the three methods and then code them. I wanted to go through them one by one, because if I go give an overview to you, I'm pretty sure that most of it will go on top of your head. Like you won't be able to appreciate the statements I would be making. So it is actually important to demonstrate every method one by one and draw the contrast uh, in that way. I could like it is important for us to write everything. I'll write the code for you. We'll do it. If this does not happen in the course of today's lecture, we'll extend this to next time, but we'll do it hands-on. You can watch through the lectures and you'll see that your this doubt gets clarified. So just wait for some time. Okay, we'll see that. So essentially, now we are in the computational part of it. Computational means earlier we had unknown was theta of x given the PDE, given a differential. Let me not say PDE. Let me say DE, differential equation, and boundary conditions. Now I have broken down the problem into uh, n unknowns into n theta I and unknown theta I values minus two values from the boundary condition. Everyone gets that, right? Right? From the boundary conditions, you will. So you essentially earlier you had a function, but now you have only n minus two unknowns to be solved for. Okay. Now, how do you solve this system of equation? This has become a system of equation, right? You have so many variables, and you have n minus two unknowns and n minus two simple equations. Simple equations, or yeah, simple equations. This is something like a plus b plus c is 3, then a minus b plus 2c is 5, and a plus 2 plus c is 0, let's say. Okay, so this is of similar sorts, right? You see that this, just because I have added xi, I have added I, so this holds for all I also, for all I. So there are n equations, and actually we have n-2 equations and two boundary conditions. So n unknowns and n equations, right? So how do you solve this system of equation? Can anyone shed some light on this? So now I'm taking this much time to just emphasize that even if we solve, if we go by the simplest approximation method, finite difference, at some point we are struck by this problem that we need to solve a system of equations. And that is essentially what week 3 is about. So the next 2 weeks is about solving it's a linear algebra problem. So the next 2 weeks will be about the numerical methods in linear algebra. So that is what we need to do there. So now while while we code, while we code, I'm not going to uh, go into or dwell into how do we solve the system of equation, but because we are doing things in Python, there are libraries for everything. We're just going to apply those libraries and not uh, be concerned about how they did it. We'll just say that they did it. Let us outsource that part of the problem, and let's see the philosophy of finite difference. Let's code this thing out. So at this point, I'll just one last thing before we go into the coding part of it is we have to write just to standardize this process. See, uh, next, just like how Bhanu said, um, that once this problem changes, some other problem changes, we don't want to do the formulation again and again and write the code every time. We want to standardize also. So to give it into a standard form so that our finite difference scheme becomes a standard. We write one code for the entire scheme and that's it. We don't write a second code for it. For that, we need to formulate the problem into a certain um, in a certain uh, what do you say, in a certain fashion. And so that is what we will do. So the way what we will see is these equations can be actually written in this form, ax equals to b. This is the fundamental equation that we deal with in linear algebra. Okay, where x is a vector, where x is actually, let me not say vector, let me say a list of all unknowns, of list of all unknowns. So what are our unknowns in this case? Can you tell? Is it xi? What are our unknowns here? So note, let me point that out. List of unknowns. Actually, no. A list of unknowns are not xi's. So it's actually theta i's. We don't know theta values. We know xi values. Xi values is something that we can choose. So suppose I discretize my domain 0 to 1 into 10 space into 10 into 11 nodes. So I know 0, 0.1, 0.2 up till to 1. These will be our xi values, but unknowns will be theta i's. That is one thing. Then what is A? A will capture the coefficients in all our n equations. So because ax equals to b is capturing n equations, and what essentially is happening there is that given some ith equation, okay, some ith equation is given. So let's say this is the ith equation, right? This is the ith equation. Ith equation is, or let me write couple of equations first. Okay, let me write the first few equations for us, all of us. What is the first equation that is there? That theta of 0 is 0. This is coming from the boundary condition, the first boundary condition. What will be our second system of equation? It will be this: theta of 2 minus theta of 1 divided by theta of 0 is theta of x1. So x1 we know is so let me also write that. So what will be our xi's? Xi's will be I divided by n. So how am I writing that? Um, suppose I write it as n plus 1. Okay, so this will be, then this will be right. If I break 0 to 1 into n plus 1 nodes, okay, n plus 1 nodes, then the gap will be I. So you get this, right? Xi will be I divided by n. So it will start from 0, then 1 by n, 2 by n, and so on, right? And then last will be 1. So if I take an example of 3, let's say n we take 4 points. So then 4 point, if I want to break things into 4 points, then this will be 1 by 3, 0, 1 by 3, 2 by 3, and then 1. These are 4 points, right? That's why this is, if I want to break it into 4 terms, then actually I have to, if I want to break it into, this is 4 terms, right? If I want to break it into 5 terms, then this will be 1 by 4, 2 by 4, 3 by 4. Pretty simple. This is, I'm just emphasizing. These will be 5 points. So just wanted to note that. So xi is I know, theta 0 is known. So this xi value will be I by n, right? This will be my first equation. So I will be 1. This is my second equation. I was 1 here. Okay. This can you appreciate that I'm writing the correct equation, or if have I made any mistakes somewhere? And can anyone please note that? What is delta n also is something that we can write actually. So this will be 1 by n, or 1 by n square. This is also important. Delta x is also 1 by n square. Okay, that is also something. Can substitute. This will be x2. Guys, you're able to get this, right? How am I able to write this equation? These three equations, the first three equations that I have written, that makes sense for you, right? No, should I properly do it? I think yeah, probably you got it. Now every time the governing equation changes, the differential equation that we are solving changes. We don't want to us to always code these things. So what we do is this is how I will write this. Okay, so I'm showing it to you only for the, let's say theta 4 is this. Let's say theta 4 is a 1. Or let me not write theta 4. Let's say these three equations. How will I cast these three equations into this ax by b format? Let us talk about that also quickly. So the way I will do it is I will write, let me write this using pen other than, yeah. So first of all, I will write it like this. I'll say theta of 0, then theta of 1, then theta of 2, and then theta of 3 I have not written, but let me write theta of 3. And then this will be the right hand side. So ax equals to b represents the right hand side. You will see. Now you see in the first equation, only one term is coming, which is theta of 0. So I'll substitute 1 and I'll write 0, 0, 0. And if I multiply this thing and see, we will see that theta of 0 is equals to 0. Okay. Theta of 1, the first equation, the second equation, we will write theta, the coefficient, and the coefficient for theta of x of 0. What is the coefficient? The coefficient is n square, right? 1 by n square, so n square. Then this one is minus 2n square. So this will be 2 to n square. Then this will be n square again, and this will be 0, 0. No matter how many points are there, something. What is the right hand side? It will be e to the power 1 by n. Okay. What will be the second equation? So if you multiply, what you will the entry you will be here, the entry, whatever the entry will be here, gets multiplied by theta of 0 in the second equation. There is no entry of theta of 0 here. So you have 0 here. What about theta of 1? You have n square. Next is minus 2n square. then n square, and so on. So you see now we can construct a, then and we can construct a b also. So the b second entry in b will be e to 2 by n. Now if I have a and if I have b, then I can calculate x using linear algebra algorithms. Okay, this is given for us. So whatever is left for us to do is construct a, find b, or construct b and just find x, and that will give us the values of theta. Okay, before I do that aspect also, before I do that aspect, let's also derive the exact solution of this equation, because the reason we have taken this equation, and whatever I'm doing, again, one more thing, whatever I'm doing, I have actually taken everything from this paper. You can go through this paper also. This paper is solving the same problem. I've just taken this paper, so you can refer to this paper if you would like. Very simple to follow paper, but a very fundamental paper, I must say. Very good paper. You can go through it. Very fun, very easy to understand, but it will take you will need some time to spend on it. Or uh, or you can just simply watch this part of it, because we are also doing the same thing. So you can just follow whatever we are doing. So just before I go into the coding part of it, let's just quickly derive the exact solution. At this point, for this problem, we can actually find the exact solution also. So just quickly, theta dash will be e to the power x plus c, and then theta double dash will be theta will be e to the power x cx plus c2. Well, yeah. Now we know the two boundary conditions are theta of 0 is 0. So theta of 0 is 0. So this becomes e to the power 0 is 1 plus c of 0 is 0. So c2 you know is -1. Okay. Then theta of 1 is 1. So E plus C plus this is -1, right? C2 is -1 becomes 1. So this becomes C. The value of C you get is as 2 minus E. Okay. So the exact solution becomes e to the power x plus 2 minus E x plus -1. Let me just check if I have done it correctly or have I made a mistake. I think I've done it fine. Let's check in the paper only. What is the exact solution? Yeah, see, so they have taken instead of x, they have taken eta. But yeah, so the exact solution is also there. Okay, now let's start coding. So we'll go to a Jupyter notebook and we'll code the thing there. Okay. Whenever there are two important libraries, whenever you start coding in a Jupyter notebook, there are two important libraries that you can always assume that will come handy, or that you will require to um, that you will require them to be used is NumPy, which is for arrays and other things, and matplotlib. This is for plotting. Once we substitute, once we get our theta values, we want to visualize them also. So we want to plot them with respect to x, and we'll see if it follows the theta of x curves or not. So there it will come in handy as handy. So we'll see that. So this is first thing. Now we'll implement finite difference method. Okay. So all formulation and everything we had done. What we have to do is first note that we have to identify what are x. First we find our x values, right? So for that there is this function of linspace where you get it as 0, 1 and n. So you define n. What is your n? Let's say 10, and we'll keep it as n plus 1 rather than n. Let's see what our x comes out to be. So x comes like 0, 0.1, 0.2, and this thing. Okay. Next, what we do is, because we also have theta. Now, given the number of nodes, we have n plus 1 nodes, right? Uh, how many unknowns will be there? There will be theta. There are also let me put it boundary conditions. The next thing is, let's look at boundary conditions. We put boundary conditions also. So boundary conditions. So boundary condition 1 is theta 0 is 0, theta 1 is 1. So I'm just writing this wherever I have to implement this boundary condition, I'll use theta 0 instead of 0. Okay. Then the next thing is constructing A. So let's construct A and B. And B. Everyone is able to follow. Am I coding too fast? Probably not. So now what we'll do is, you see that if you have n unknowns and n equations, you need a will be of this sort. So you use np.zeros. This function creates a 2D array. If you give this input, actually we have n plus 1 unknowns and n plus 1, and so we have n plus 1 unknowns, right? X has, and this has 11 unknowns. Just to check, let's see, we have these 4 values, right? So n plus 1 unknowns are there. So A will be of size n plus 1 cross n plus 1. B will be of size np.0 is n plus 1. So let's look at how A looks. A looks, and then print A, or let me just write A, and let me just write B. So let's start with only 3 points. So yeah, this is how it looks. Okay. Now theta um, will be again, theta will be of the same my dimension as B. Okay. Now there is this now we need to put in values in A and B. Okay, so let's because the way we have done this is, let's come back to this. The way we have done this is that for every I we have one equation. So we'll run in a we'll implement a for loop. We'll run a loop and implement this entire thing into this thing. We'll for every time we'll for every I we'll update the entries in A and B. So before that, one more thing which is important here is that del x in this case is what? Del x is what? 1 by n, and this is x. So you agree, right? Del x, let's check what del x is. Del x is this 0.333, right? If I have 10 points, 11 points, then del x will be 0.1, right? So let's start with 4 points. For I in range, this is how you run a loop in Python. How long do you want to run it? For n plus 1 times, right? This one. Every time you note that you're dealing with only 3 elements. See, every time you are assigning coefficients for the ith one, I minus 1, and I plus 1. Okay. So uh, if no, actually you just write a of I. So ith element will be minus 2 into divide by del x square. This is how you write square there. I minus 1 is 1 divided by del x. Guys, you're able to follow. Should I slow down? Should I emphasize, like, should I spend some time on something? Are you guys able to follow? And again, let's write bi also. So bi, there is no second index for bi. Bi is simply e to the power. So np.x. This is how you write exponential in Python. You can right? You can use NumPy, and then you write I divided by n. You see, I told you, right? Xi is 1 by I by n. So this will be I by n. Okay. Okay. So this I, let me, before running this loop, let me just show it to you how I runs. So print I. So this will run from 0 to 4. It will run 5 times, which is okay, right? It's not okay yet. So 0, 1. How many elements are there? 0, 1, 2, 3, 4. So it's okay. Yes, this is fine. So this is how it will run, right? Or let me just put it as xi. So let's look out at what node we are looking at. So we start at 0, then we go to 0.25, then we go to 4.5, then 0.75 and 0.1. This is our x. Okay, 5 times we run it. Uh, should I go ahead and run this loop? Anyone has any comments?
Yeah, you can run it.
No, we cannot run it because I have not taken care of the boundary condition. See, at I equals to 0, there is no I minus 1. There is no left point, right? And at I equals to n, the last point, there is no I plus 1. Yeah. So for that, we will have to take.
Basically, I was having this doubt only. Sorry to
Okay.
interrupt.
Mm-hmm.
It's like basically when we were deriving this one,
Sorry, couldn't
we'll
hear
take
you
the
properly.
if we consider the theta. Hello,
Now there's a little bit of
hello.
jitter. Now it is better, it seems.
Yeah. Uh, Suppose if we are considering theory points to solve this, like theta I minus one, theta I plus one.
Hmm.
If we are considering the theta I,
Hmm.
so we need the boundary conditions of theta I minus one, theta I plus one,
Sorry, Yashwant, can you
right?
type in your question? Can you type in your question? There is a lot of can't hear him
Yeah, yeah,
properly.
yeah,
Bhanu,
yeah, yeah.
there's a problem with on your end also, right? You can't hear him, right, properly, or is it only my issue? Let me just type in. Probably, I understood your question. You're asking something about the boundary condition. I didn't properly understand it, but almost was able to hear you properly, but didn't get it. You're writing your thing in the chat, right?
Yes, I'll try to explain in the chat.
Great, great. Meanwhile, okay, wait, I'll wait for it. We're also out of time. So good. We can spend some more time on finite element next time. It will be very nice. Actually, I also read about finite element. Uh, it is very different from
Yes.
finite.
Is it audible now? Because I think while typing it can't be communicable. Like I could
Okay,
not
yeah, go
explain.
ahead. Let us try
My
one more time.
question,
Yeah.
yeah,
Hmm.
is it am I audible?
Yeah.
So the question I was asking is to solve the problem, we need the boundary conditions at theta I minus one and theta I plus one, right?
For every I.
Yeah, for every I. Is that
Okay.
that is how we solve the problem, right? Finite difference. Suppose if we
Uh,
are taking theta
hmm.
I, we go back,
Yeah.
yeah. So we
Hmm.
have 3 points.
Yes. Yes.
So the leftmost is theta I, yeah, that one, that figure, yeah. Theta
Yeah.
I minus one, theta I plus one.
Yeah.
Suppose if we want to at theta I minus one, we have the boundary condition. At theta I plus one, we have the boundary condition. We need to find the theta I value. We are going to find the theta I value.
That is how you're looking at it, right?
Yeah, yeah.
It is actually, yeah. So this idea was it is actually that it is this idea that Yeah. So when we were writing this
No,
whenever
basically
we were
my question is not completed. Like,
okay, okay, okay.
basically my dad, I was just ask, that is basically that is what my interpretation is. I'll explain first,
Hmm.
and later I'll ask. So basically we are finding theta I value
Mm-hmm.
by knowing the theta I minus one values and theta I plus one values. So this is fine at when. So my question here is, when we come at the boundary condition, like at suppose at the end of the boundary condition,
Mm-hmm.
theta I, suppose if you are considering theta I plus one as a boundary condition,
Hmm.
so there also we need 3 points, right? Like, what will be the right next point?
Yeah, I get your point. I get your point. See, that is what I wanted to emphasize on this. Whenever we are writing these equations, we are always having a right end point. I'm not gonna call it a boundary condition, okay? Because boundary condition is different from theta I plus one or theta I minus one. First of all, I'll explain what boundary conditions are.
Yeah,
But
yeah, okay,
your
okay,
point
understood.
is the point is correct though that at boundary nodes, how do you enforce this this condition? How do you enforce this? Uh, and
Yes, yes, exactly
the
that.
sim
That
the
was my question.
simple answer is that we do not enforce in a finite difference scheme. We do not enforce the governing equation at the boundary nodes, and that is what this paper is actually about. If you go through this paper, you will find actually this paper, and this is a very like a very latest paper. Okay, it is a 2015 paper, 16. See, and this paper talks about how, and this is something which is not discussed in textbooks, that uh, in principle, by not enforcing this condition at the at the boundary nodes, at the leftest point and the rightest point, we are in a sense we are not conserving, or we are not um, we are not satisfying the governing equation at the boundary nodes, and so our conservation laws will get violated. There will be an imbalance in our different terms in the conservation statements. And the reason is, see, the reason, if we try to implement this, if we try to implement this, uh, if we try to implement this as well as the boundary condition. So see, at the rightest node and the leftest node, you already have some information which is given to you as a boundary condition. So it is boundary conditions are only the leftest point and the rightest point in a 1D simulation. Okay. So now the thing is that you know a lot of information already there, and the way this approximation is made, see, the issue is, the flaw is in our assumption that we can specify a function only by the nodal values at some discrete points in the space. There is the issue is there, because in the exact solution, both things are true. Boundary condition is also true, and the governing equation is also being satisfied. But in a finite difference method, because the way we have approximated things and the information that is available to us, or the information that we want to find is the nodal values, we can't use both of these criteria. First of all, we don't have theta I minus 1 or theta n plus 1. And second of all, if suppose I have that, suppose I give it to you, suppose I have some information, then the number of unknowns become less than number of knowns or number of equations. So boundary conditions, if you treat boundary conditions as also equations, then what you will have is the unknowns are n minus 2, or let's say n, and your number of equations will be n plus 2, because n equations from coming from this, and then two equations from the boundary condition. So the essence, what in a finite difference scheme, because we know that the boundary condition, we know the values at the boundary condition, we know the values at the boundary nodes. That is why we choose not to implement this at the boundary nodes, but rather enforce boundary conditions at the boundary nodes. Did I make some sense there? Because I think I used boundary
So
or nodes. Yeah.
yeah, basically what I understood is, basically in finite difference method, in basic sense, we can't apply this formulation in at boundary conditions. This is what you are.
Yes, and if you think about it, see, if you think about it, actually we don't need to also at boundary
Yeah, yeah.
because we this essentially we are doing this to find the value at theta I or theta xi, right? So there is no need to enforce this because you know the information there. You get my point, right? So that is there.
Yes, yes.
Okay. Now I have only 5 minutes to left. Let's see how much we can do it. Then we'll close. We'll continue from this in the next time. But we will have to take care of the boundary nodes as Kishore discussed. So for the case of I equals to 0 and we use I or when we want the same thing. So I'll first write the thing there. Then what we want to do is I is 0, then what you do is you write AII is 1. Does it make sense why AII should be 1? Can anyone tell me why? See, once I write the next line, you will be able to get it. So B equals to 0 will be theta of 0. And let me not write this. So in Python, you can actually write -1 for the last element. Okay. Here. Now, why AII is 1? Because you note the boundary condition, if written as a equation, is 1 into theta of 0 is 0. And 1 into theta of n, theta of what do you rate? N is 1, right? So that is how you do it. And once you write it, see, the element here will be 1. Again, the last element will be 1. Okay, so now let's see how A looks and B looks. Okay, let's see. See, delta x, see, this is how this matrix will look. Let's also see how B will look. B also will look something like this. Now there is this function in Python where you can just simply write theta equals to np dot lin algebra A comma B. I think this is what it is. No. Is this one? No, I think what is this?
Linear algebra, I think it is for determinant finding. Is it not?
Lin algebra dot solve it is. Okay, dot solve. Now it will solve it for you. Theta is plt dot plot x comma theta. Let's see. So it's coming like this. Let's also plot plt dot plot x comma the exact solution which was there. Okay, which was e to the power x. So np dot exp x plus 2 minus np dot exp of 1. This was the exact solution I'm writing. Minus 1. Let's see. See how these two matches precisely, very correctly it matches. Now let me increase it and increase it for a large number. Okay. Okay. It will be very smooth. Okay. So this is the solution that we were supposed to get, and we are getting that solution. I'll show it to you. scatter. So let me do it for 10 elements only. See, so this is, let me put color equals to 0. See, but yeah. Very simple example. Okay, this is a very simple example to be. So this is, you see, the exact solution and the finite difference method is this. Okay, you might think that this method is invincible. You're getting very correct solutions and anything, but we'll talk about what is going on there. There are few caveats also. Okay, you see how I have just plotted. Let's discuss that part in the next time. I'll leave this up till here, and let's talk more on this and other schemes later on. I'll just type in today's date here. This is 5th August 25. Okay, so maybe we'll meet next time. See you, and yeah, if you have any questions, we can discuss. Otherwise, we can, yeah, leave. Thanks. Thank you, Yashwant. Thank you so much.